That was a good quote. I don't even remember saying that, but it sounds good, so it must have been me. So, so thank you all for being here today. It's a pleasure to be here to talk with you all at Villanova Law. This is perhaps going to be a little bit more of a meditation, a reflection on where we are today in our thinking about algorithms. It's a framework I use a lot in my own thinking, so I'm hoping to share that with you as a way to kind of make sense of some of the discussions we're seeing in the world about AI. I will say that I had promised some folks there'll be no math, but I lied. There's one slide with math on it. This is why you can't trust a computer scientist, so just be warned, but I will explain. So I think it goes without saying that we're seeing a number of different examples. I could refresh the slide every week with new vignettes about what I'll call the collisions between algorithms and society, whether it's about using automated systems to do identity verification, or building these algorithms to do tenant screening that have these unfortunate biases associated with them, whether we're talking about social media platforms that are addictive and harming children's mental health, whether we have chatbots sort of making fake news, and especially with the election coming up, lots of fake information about the election. There's more I could say about that and about the reliability or lack of reliability of election information coming from chatbots. And as well as data breaches and other things. What we're seeing is a series of, dare I say, problems, challenges, as we increasingly bring algorithms and AI into our world. One of the things I like to think of as an academic we try to do is make sense of these situations, try to get beyond the chatter and the moment and the hype and the fear to say, okay, what is really going on, right? So what is really going on? Why do we continue to have all these problems with algorithms? And as probably comes as no surprise to all of you, there are many, many answers to that question. None of them are wrong, but they all address certain aspects of the story. For example, there is a long-running concern around biases in society to the large extent that machine learning and AI systems absorb a lot of historical data to build their predictive models and their behaviors. They're going to reflect and amplify biases that exist in that data and that historical data in society. So that's one problem. There's the usual you're using it wrong kind of argument to the user error that we as humans we are unable to understand how to use modern technology, and if we just knew how to use it better, many of our problems would go away. There is the idea that we don't have enough protections in place. I mean, this is, of course, an argument I'm at least somewhat partial to because of the work I did, that we don't have the kind of guardrails to make sense of this new environment we're in. Kind of like how when cars first came on the road, we needed rules. We need literal guardrails. We need lanes. We need driver's licenses. We need all these things to make sure we could take advantage of transportation without all the associated harms. There's an argument, maybe a more market-driven argument, that there are misaligned incentives. There are incentives for companies to put out tools, to put out products out there that are maybe not as well finished as they should be, because there is no incentive, no economic incentive for them not to do so. And that has to come from the market in some form or the other. And so that's another concern that maybe we need to rethink how we design our markets, how we design incentives, how we sort of set up marketplaces for this purpose. And another argument that comes up is that we have problems with algorithms because algorithms do not speak to all of us. That algorithms designed for the most part in San Francisco are designed to optimize for the white 22-year-old male who writes code in the Silicon Valley and needs tools for that. And if we don't have all the voices of people who are affected by technology in the room, we are unlikely to be able to design technology that serves everyone. So like I said, all of these arguments make certain sense and have certain relevance in certain sectors, and none of them are wrong. And depending on where you sort of stand, you might sort of see your role or might see your ability to intervene in one of these different sort of areas. I'm a computer scientist, and for me, a lot of the question that I come back to is there something fundamental about how my field has changed, the field that has produced all of this technology, that needs to be re-examined so that we can build better, we can reimagine and redesign, which is for a reason why it's in the name of the center that I direct. And I think there is an argument there. And it goes to the idea that computer science as a field now has gone beyond its origins, its roots. It is now a socio-technical discipline. So this is courtesy of my colleague, Seni Kamara. So if you think about most of the at least up to the early 2000s, the primary sort of value proposition of computer science was efficiency. We can make things faster, we can solve problems that are hard to solve by people, and we can do this using magic, using mathematics, using computers, using whatever we want. And this was very, very successful. We built the internet, we built the web, we did a whole bunch of things that affected our human productivity. In the case of the web, the productivity effect maybe down versus up, but that's a different story. But it affected us in many ways. And soon it became clear that the tools we had started to develop, in early days it was game theory, mechanism design for advertising, things like expressing complex, thick notions like privacy in the language of computer science, and then more, last 10, 15 years, moving into things like decision-making and recommendations. We began to sort of believe that we could use the tools of computer science, in particular the tools of machine learning and AI, and I'll use those terms interchangeably, to affect human lives as well. In other words, CS as a discipline that was built and designed for doing more technical work had become a socio-technical discipline. In my view, this is the source of the challenges we face right now, the need to recognize this point. But what does it mean for something to be socio-technical? It's a term that actually gets bandied around a lot right now. If you look at a lot of government documents coming out around AI, you'll see the word socio-technical pop up all the time. I will take at least a little bit of the blame for that, but I think it's an important term because it refers to, and I saw a handbook of STS in Brett's office, so yeah, So this idea of a socio-technical system is idea of a system that intermeshes digital technology, people, and institutions in society. It is this intermingled system that controls and shapes how we live and thrive. It is not just take a system, put a piece of tech in, declare victory, and go home. And that if we have to understand what happens when we bring technology into the world that we all live in, that we've organized a certain way, we have to understand these systems as intermingled, not as separate from each other. And that is the whole idea of socio-technical systems, the idea of the scholarly field of science, technology, and society, and the way in which we have to, when we take a problem we're trying to solve, think about the stakeholders, think about who has the incentives, think about who's being impacted, and so on. And this sort of, has found its way even into the way, at least this administration, has tried to think about AI policy broadly, right? So the blueprint, of course, as Steve mentioned, was sort of a foundational document coming out of the Office of Science and Technology Policy to sort of articulate what protections we need in a world that is increasingly algorithmic. I'm not going to go into too much detail on the blueprint itself. Suffice it to say that, the main document or the core part of it is these 5 principles that systems that we build should be safe, they should be effective, they should not harm, and they should do what they claim to do. They should not discriminate. Our data should be carefully curated and managed and not used indiscriminately. We have a right to know when systems are being used that affect our lives and how they're being used. And then we have a right to sort of a human alternative, a sort of a dial zero for operator, right? Because systems fail, and they do fail. And I know this because I build some of these systems and they break all the time. We need backup options. We can't rely on these entirely. These are very simple principles. They sort of draw on things, good practices and concepts that people have talked about for a long time. And I wouldn't call them novel in any sense. But it was helpful to articulate them because that has helped articulate more specific, more concrete government actions, such as the very important executive order on AI that the Biden administration put out last year. That's, I think, a very long executive order, precisely because it has to cover all the ways in which AI is touching different aspects of US government sort of actions on this. The idea of this sort of thinking about socio-technical systems, thinking about what it means to integrate algorithms and technology into the way we function as people. It sort of has very subtly implies, and so subtly that now that when I tell you about this, you'll see it everywhere, but till I recognize this phenomenon, it was hard to put a finger on what these assumptions were that people are making when they wanted to use algorithms to, say, predict whether someone should be released on their own recognizance or not given bail, whether someone should be hired or not hired for a job, and so on. And I package all of this up together in what I call the algorithmic lens. That when we solve or when we try to intervene in social systems now, more and more we are using this lens. I will say more about this, but I use the word lens deliberately because, I like lenses. I have one. They simplify. They make assumptions about the world. And the world we see through the lens is much easier to understand and intervene than the one without, where you're all a bunch of blurs. So lenses are important. They distort, they sharpen, and they focus. And so if you want to understand if you want to understand what this lens is doing for you, if you want to understand its power, you must also understand its limits, what you cannot see as a result of the lens. This is a core notion in computer science, that in order to understand the power of a system, you have to also understand the limits of that system. And it is only in doing that dual work that you fully can say, I understand what this is doing. And understanding the limits is not an attempt to bound it. It's to say, okay, this is where I should not go. This is where I should not go. This is where I can go. And we have to do that in order to be most effective at using algorithms where we can, putting protections around it where it might have problems, and saying, no, this is not an appropriate place for technology when we don't. And if we don't do that, we will continue to be in what I call a sort of whack-a-mole mode where someone tries something, it fails, everyone says, see, we told you, algorithms will fail. And then we try it again and again and again and again. It doesn't feel like we're learning anything if we do that. And this goes back to the very earliest days of the field, right? I mean, you've probably all heard of Alan Turing. You may have heard of the Turing test, this sort of test for whether a machine can behave like a person. That's all everyone can talk about right now with LLMs. You probably haven't heard as much about the Turing machine, but you may have, his sort of idealization of a computational device. And I like to think of these two as sort of in juxtaposition to each other when I talk about power of the limits, right? The Turing test was his way of trying to say, what does it mean for a machine to be like a human? What does artificial intelligence even mean? It's a discussion we're having right now. And he talked about this in terms of simulation, whether you could have a machine that could fool a person into believing it was human. But he also came up with this notion of a Turing machine. And the first thing he did with it, with this mathematical abstraction, was to show what you could not do with computers. And almost at the same time, he did both things. So on the one hand, these machines could be as powerful as people, and here's a way to test for that. On the other hand, I can tell you something very simple that no machine can do, regardless of how fancily you build it and how many GPUs you put in it. It does not matter. The problem itself is very simple, by the way. If you haven't heard of it, it's called the halting problem. It says, I'll give you a program and give you an input to the program, and I feed it in, will it ever stop? It seems like the most basic thing you should be able to know about how a program functions. And he showed that no computer could solve this problem for any program and for any input. It's called the halting problem. So again, to understand the power, we need to understand the limits. So let me first start by sort of fleshing out what this algorithmic lens is, how it helps us look at the world, and what its limits are. And then we'll see what we can do with that information. Okay. So if you had to capture what this lens looks like, and this has sort of come up because I would have conversations with someone who was trying to use AI to solve some problem, and I would talk to them, and I would sort of say, okay, what is it you're trying to do here? Eventually, what they would come up with is something like this. That the core idea of this algorithmic lens is that somehow we can create a precise formulation of a societal problem that we can find a single best answer to. Now, I want to highlight a bunch of key words in this, because I think they're important. First of all, what makes this interesting and tricky and powerful and dangerous at the same time is that we're talking about a societal problem. I'm not talking about, optimizing the path to get me from here to the airport. That's important, but it's a different kind of problem. There are societal issues there, but I won't get into that right now. But that's a problem you teach in sort of undergrad algorithms. How do you find shortest paths between A and B? I'm talking about societal problems, whether someone should be admitted to college, or what kind of loans we should be giving out and to whom, and so on. And we also have different ways to find this answer to this problem, usually by solving some kind of math problem, designing some kind of mechanism that will evolve to an equilibrium that will solve a problem, like we do with ads, or more currently, optimizing over data. And a couple of key words that sort of are the signifiers of this lens are that we believe we can find a precise formulation, and I'll say more about each of these little highlights in a second, that we can find a single answer, and that this is, under some definition, the best answer. Again, I want to emphasize, if I talk to maybe folks in this room or even computer scientists in the world, this is taken for granted. That, well, yeah, of course, this is what we're going to do. There is no question that this is exactly what the goal is. And again, I want to emphasize the optimizing of data. There's also a more subtle point here, which brings in the socio-technical aspect of this. I said we. It's rarely clear who the we is. And often asking some hard questions about the we starts forcing you to ask questions about who's building, for whom, who's being impacted, which makes it very important then to figure out where in society the system is being inserted. So let me go into these elements of the lens in more detail, just explain them. So the first one is precision. And again, if you've ever had to design an algorithm to solve any problem, you will know this, that the first thing you have to do if you want to design a machine learning system is to figure out how to represent your data. That's a lot of words for how do I convert whatever information I have, whether it's text, whether it's video, whether it's anything, into a bunch of zeros and ones. This is more subtle than it might seem. So, we were talking at dinner yesterday about these algorithms that are used to predict whether someone should be released on bail or not. And then one question comes up as well, you want to look at evidence of prior crime as maybe an indicator that maybe this person will go out and commit some new crime if they're released on bail, and they perhaps shouldn't be. Okay, but what is evidence of prior crime? You need something precise. I can't just say evidence of prior crime. I can talk about it maybe in a courtroom, but I can't put that into a piece of code. It's like, oh, well, we'll record the number of prior convictions. Okay, maybe we can get some data on that, but how many prior convictions? Do you want to record all in the last 3 years? Do you want to record the number of years in which you've had at least 2? Now, these all seem like nitpicking, but you have to be specific because you have to be precise. You have to be extremely clear as to exactly how you're encoding your data to put into the system. And then once you do that, you can do all the training to produce an output. And of course, this implies that you're getting all that precision from somewhere in data. And there is a sort of a bedrock assumption through all of machine learning. People will think I'm crazy if I question this. That says, more data, more fun. In data we trust. The more data we can get, the better. If we can't get enough data, we just have to find it somewhere, and we'll get it. This is a core assumption. Okay? I'm not yet here to critique these assumptions. I just want to tell you they're very important parts of how you build these systems. Because this leads to the desire to collect different kinds of data, the list of more data, and that's where this impetus comes from. A slightly more subtle assumption, subtle because it's again so deeply ingrained that we don't even question it, and people have looked at me strangely when I said, so how do you know this is true, is that there is some answer to be found, some kind of single truth. There is, in fact, the best person to hire for the job, and it's well-defined. We just have to get the right amount of data and express it precisely. Right? This is motivated by many things. One thing it's motivated by is scale, that if you can automate this process of finding the answer, you can do this at scale. You can do this for thousands and thousands and hundreds of thousands and millions of cases. It also makes a certain assumption that we are, in a sense, we can be flattened, that all the relevant information about all of us in this room, with all the different, our personalities, the clothes we're wearing, our backgrounds, can be flattened into some precise description with enough data that some decision can be made about us. That from the eyes of the algorithm, we are all the same at some level, depending on how we're encoded. So there's a kind of homogeneity that comes along with that assumption. And finally, this is one slide now, that not only is this answer out there, that we can find it. So computer science is all about doing things, right? It's not enough to say there exists an answer. That's the mathematician's job. It's a computer scientist's job to say, okay, fine, how do I get it? And the answer in the algorithms is by optimization. In other words, find a way to say, I can go down a hill, and at the bottom of the hill is the thing I'm looking for, informally. Formally, the idea is you write down some cost function, some function that says, in this particular case, in the first example, this is what every intro machine learning class has a slide that looks like this, that says, I have some inputs, the data, X. I have some desired output, the Y, that's my training data. And I want to build a way to figure out from an X what the Y should be. Well, it's like I have the answers to the questions, those are the Ys. I want my magic function F to figure out what the Y should be. So I search over all the Fs in my space to find the one that gives me the best answer. And what's the best answer? The one that disagrees with my given answers the least. So that's called accuracy. And so there's all this technology to to find the best such function possible. And this is a very powerful framework because once you have that framework of optimization, you can add in other things into it to express other constraints. So you might say, well, I want an accurate answer, but I want this to be explainable so I can explain it to someone to say, this is why this decision was made. So you can throw in some other term to say, okay, you want to minimize a combination of things. So you get these very baroque, long expressions of things you're minimizing and some engine that optimizes them in order to do this. So it's not just that you believe there is an answer to be found, that it's the best answer to be found, but that you can find it. And this, by the way, is an absolute lie in the sense that all of these problems, remember I told you about Turing and the Turing test? We can show that most of these problems we want to solve are actually intractable. You cannot solve them. You can hope to get close in some circumstances, but most of the time you can't even guarantee that. So it's almost like saying instead of having a single hill that you go down to get to the bottom, it's more like there's a whole bunch of hills and valleys. And you just get somewhere and hope for the best. But I'm running ahead of myself. This idea of optimization at the core of what our design principle is about is not a new idea. There's a very nice book called System Error by folks from Stanford that sort of talks about this. One chapter is exactly this, the optimization mindset. Right? The idea that if we focus on efficiency and we focus on optimization and we apply that focus on efficiency and optimization to societal problems, then the problems of optimization become our problems as well, as they say. So just to summarize, right, we have this components of the lens. We have precision, we have data, we have this idea of the universal solution, the single answer that gets us what we want, and we have this way to get there by optimization. What are the problems with this? So I've sort of started to hint at that, but I haven't really gone into it. But what are the issues with this? And the reason why I think this is, again, important is because the algorithmic lens is not the only such lens we use in the world to make sense of it. There are many lenses over the decades. And a couple of lenses that I've sort of found very compelling are one from physics. I don't know if you've taken a physics class and heard of the spherical cow. Anyone ever heard of a spherical cow? No one. One person, two maybe, yeah. So you're doing intro to physics and you're trying to sort of understand how objects move, you'll make certain idealizing assumptions. And so one of the running jokes in the physics class is assume a spherical cow. Because then it makes your life easier to do the calculations to understand how things move. Assume a frictionless surface. Surfaces are not frictionless, but you can assume it for the purpose of doing this. It's a lens sort of an idealized assumption, a lens you make to sort of make inferences about the world. And it's a good lens, you can do things with it. Not all cows are spherical, but it helps you model certain problems in certain ways. There is, of course, the classic, somewhat old now, economic model of the rational man, right? Always the man and always rational. That you'll assume that people always function according to their own self-interest in the most rational way possible, and we can model how people behave based on that. It's a lens. Again, I'm not saying it's a bad lens, but it's a particular way of looking at the world. And there's this very nice book by Michael Sandel, which talks about the limits of markets. And if we think of a market-driven approach to sort of solving all problems, are there any limits on this approach? Are there things that markets cannot do? Right? So again, all of these things talk about both a framework, but the limits to that framework. And that's why I sort of invoke that here when I want to talk about the limits of the algorithmic lens itself. So there are many examples. So we talked about precision, the idea that you can precisely, excuse me, that you can precisely encode information about people. This turns out to be harder than you think. So one such example is about, encoding gender binaries, right? As this is not as simple as one might like it to be. Having a little binary attribute 0, 1, male or female does in fact not help deal with many of the problems we have with representing people fully into the fullest extent of their lives. It's not just with gender, things like race, things like other aspects of your life. Forcing it into a set of categories tends to miss the complexity and the messiness of a real person's life in a way that can be problematic for certain situations like this. This issue of data, like I talked about, more data is always better. Yes, but if you have the right kind of data. One of the problems with sort of pretrial risk assessment tools has always been that it is unclear whether the data you're collecting is validated, has been collected in a sort of a somewhat rigorous and unbiased way, does not have a bunch of confounders because of how it's been collected. For example, if you collect data that is derived from police reports, then you have to assume that the way in which sort of police sort of operate and make reports itself does not have biases in it. And if they do, you're going to have problems in your output. So to the extent that your data itself is biased, more of it is not going to help you. It's going to make things worse. So this inability to sort of focus on the fact that the more data is not always better is a problem. There are other technical issues with more data, especially more kinds of data. Roughly speaking, if you have enough different kinds of data, you will find any pattern you want just by random chance. And so trying to figure out whether patterns are actually real or just sort of because of random fluctuations in high dimensional spaces is a very hard problem. And it's often not sort of regulated. Even this core idea of is there a single truth you can find gets very complicated. So one example of this is this idea of sort of emotional AI. Right? So this whole idea of emotional AI is something like, oh, I will use some kind of scanning process or some biometric measurements or facial recognition to infer things about a person's state of mind and their affect. Maybe I'm doing this as a kind of border check. I'm interviewing them at the border, and I want to use this as a lie detector. Maybe I'm doing an interview, and I want to figure out if they are, a friendly personality and things like that. The assumption is that, yeah, it might be noisy, but we'll collect enough data, we'll get diverse data sets, we'll get it from all over the world, we'll deal with cultural norms and differences, we'll somehow figure this out. But there's a sort of a body of research, a growing body of research, and this book sort of summarizes a lot of that research that suggests that the idea that there is something inside, something intrinsic, an emotion that you can scan, is itself not entirely based in neuroscience. Rather, emotions are, at least to this telling, a story we tell ourselves to explain the physiological reactions we're feeling. And that is sort of a contingent on our situation, where we are, who we're dealing with at the moment, and how we explain ourselves. One of the stories she tells in the books is about, going on a date and feeling butterflies in her stomach and thinking she was nervous for the date because she had butterflies in her stomach, and then leaving afterwards and going back home and realize she had food poisoning instead. So there's this idea but if you believe that you tell yourself stories about what the underlying physiological effects you're feeling to construct an emotion, then the idea that the emotion is something there intrinsically within you to be found is gone. It's not a valid assumption. And then the idea that you can use ML to find that does not also hold true. So this idea of universality has to be tested against, is there something there? And emotional AI is one of the more complex and troublesome examples of this, where there's a lot of desire to find something that we don't even know is there or not. The final thing I want to talk about is optimization. I mentioned this very briefly, and that, again, I was saying this at lunch or dinner yesterday, that if you think of, at a high level, all the machine learning boils down to a geometry problem. Namely, you have things, you want to separate all the blues from all the reds, and you have to draw some kind of line so that all the blues are on one side and all the reds on the other side. Now, you can't always do this. Sometimes you're going to make mistakes because there's no way to draw a straight line to get through all of them. It's not possible at all. This example, by the way, has been known since the 60s, that there's a certain kind of pattern that a straight line cannot separate. There are a couple of problems with this. First of all, it may be that you make systematic errors on points of a different shape. All the squares get misclassified while all the circles get classified correctly. That's one issue. But also, because of this choice and flexibility and how you choose, what eventually is boils down to is some kind of pick of a roulette wheel. It's like throwing a ball into a roulette wheel. It lands on some number. That's your algorithm, and that's it. This might sound a little bit more dire than it is, but let me assure you, it pretty much is that. There is no, it really is as a bumpy landscape. You throw something down, you land somewhere where it's stable, and that's it. That's your answer. And that suggests that this idea of optimization, right, that you can find the correct answer by designing a cost function, is also in doubt. In every talk I've given in the last 2 years, one question always comes up. But what about large language models? If you don't know what this picture is of a sort of a schematic of the core object in a large language model called a transformer. There's one of the attention heads. This is how the sort of one piece, and there are like millions of these things that build up the neural network that is used for training LLMs. And so that question is, has it changed everything? And it's kind of funny because on the one hand, yes, on the other hand, no, in the sense that we've turbocharged the way in which we think we're going to be using AI because of LLMs. But the problems haven't quite gone away. And let me explain. So going back to my picture with the Turing thing, I call it the Turing swing now, because we've gone, it was, at least in the 70s and 80s, we were definitely on the Turing machine side of things. We had these formal theorems, we could prove things. We could talk about the limits of the methods we had. And now we kind of moved back to the other side where it's like, oh, we can do everything. Machines are alive, they can take over the world, So, I'm waiting for the pendulum to swing back again, which it probably will, because it has over the years of AI development. But there are things that LLMs do that are very pertinent, that are very relevant to this lens. In particular, they need a lot of data, to the point where, Sam Altman is busily exhorting all of us to go out and post more so they can collect more data to train the models because they're running out of data. I kid you not, this is what he actually said at some point. They also need many knobs, parameters. They're very complicated objects, and there are many different settings. Like this is already old. I'd have to update this graph like literally every day because I think NVIDIA just put out a new version of Llama 3, which is even more parameters in it. But these are very hard numbers to even comprehend. If people who did machine learning back in the day were talking about 100 parameters, 200 parameters, this is not something you can make any sense of. These are very, very complicated things. And if anything, the way the lens is mutated in the world of LLMs has been in the following way. The hope is, again, that we can train on as much data as we can, get it from everywhere. Let's not worry about copyright. Let's just take whatever data we can, train it as far as possible without any particular task in mind. That's the key power of LLMs. They're not trained with any specific task in mind, but they're also not trained with any specific task in mind. And assume the architecture kind of works like a brain. This is the most hand-wavy part of this whole thing. And then use prompts, so literally English text, to navigate the universe of hopefully learned tasks to find the desired answer. So you want to get, a bio written for a speaker invited to your seminar. You sort of write down, okay, give me a bio for this person. Or you want to clean up your resume, and you put in a resume and have to clean it up. Or you wanted to give you some piece of code to draw a graph that you need to plot. You don't remember the language, the code for, so it generates a. There's a whole bunch of tasks, and you give these prompts, and you hope that it works. And then what happens to these lens? Well, it turns out that things change in interesting ways. On the one hand, it feels like you don't have to worry about precision as much anymore, because you don't have to express things as precisely, because you can just talk. You can just write in English. That turns out to be dangerous. It turns out that these systems can be very unstable with imprecise things like language. There was one paper from Anthropic where they were talking about how they were trying to train a sort of this constitutional AI, the system that would be helpful, harmless, and I forget one more H, would do the right thing in general. And they found out that they were trying to get it to not discriminate, and they had to say, would you please, 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 please not discriminate? And they would sort of give it an answer that would seem less biased than another one. And if you did 3 pleases, it wouldn't work as well. You'd have to have 4 of them. So, it's a little tricky, even in natural language, to sort of figure out what these systems are doing. They need, of course, way more data than we've ever had to deal with before. And that's a problem for many reasons, but also it makes the reliance on data even more than before. The way that LLMs try to solve the problem of universality, the single best answer is to just essentially hope that we have enough information to solve all the problems we need to solve. I would say the state of art of what we know for sure LLMs can and cannot do is very weak right now. And so this really is just a hope rather than a claim that LLMs can solve problem X or problem Y or problem Z. And this optimization has become a new weird kind of optimization where we need to essentially align models with our values. So we need to somehow encode our values in a numerical form that we can then optimize a model to do. If you've ever heard of RLHF or reinforcement learning, this is essentially what these models are trying to do. They're trying to sort of figure out what is it we want and then try to train the model to produce it, which, given that we can barely agree amongst each other on what we want, is sort of an ambitious task. All of this sort of leads me and has continued to sort of inform the work I do and the conversations I have, that the existence of the algorithmic lens, its limits, its blind spots, and its power mean that the following conversation has to keep happening when we are building socio-technical systems. So I call this a moral conversation. It sort of goes something like this, and I've had this happen to me over and over again now, that in order to make use of the algorithmic lens, you need precision. Precision requires choices, it requires specification, it requires an acknowledgement of limits. But choices and limits come from outside. They don't come from inside the system, they have to come from outside, from the milieu in which the system is being deployed, from discussions and engagement. And those discussions and engagement reveal values. And this also goes back on itself, right? That the power of the lens, the value of the lens, is that it forces you to have detailed conversations about things that may have been latent, because in order to use a lens, you have to make them explicit. And that process of making things explicit makes you realize a lot of the things you thought were technical issues are actually policy issues. And that you have to have that more uncomfortable discussion up front. You can't just pawn it off on the data scientist, right? Because you will not get what you expect. And that we have to be aware of this and continue to do this. And this is not for example, computer scientists are not used to doing this. They're not used to sort of having to engage in non-trivial and meaningful ways with the society around the system that they're building. As a computer scientist, I have to train my students to be willing to do that, to realize that, oh, I've decided to use this optimization function. Wait a second, that has this downstream consequences. Are you sure you want to do that, right? And that's where I will conclude with this reflection, and thanking you for listening and hoping to have some questions. There's one in the back there. Mm-hmm.
Hello, my name's Karthik. I'm a 3L at Villanova. There seems to be like a conflict between creating more ethically sound AI systems and privacy, because on the one hand, you want more data to like make it more representative and like, especially for people of color and things like that. But like, for instance, if you were to take a use case of policing and stuff, collecting more data would mean that you are constantly surveilling people, and that kind of goes against their right to privacy and things like that. So is that like an irreconcilable conflict? And how do we think through this? So
in one sense it is. And we just published a paper sort of looking at how the desire to preserve privacy can actually increase surveillance if you use these privacy-enhancing technologies, because it gives you license and sort of protects you from liability in doing so. But you're right that the impetus to not collect data makes it harder for people to be seen who need to be seen in order to mitigate problems with these systems. And I think it's interesting then to reflect on why that's a conflict. It's a conflict because collecting data is a problem. Okay, but why is collecting data a problem? Oh, because this could get used in all these different ways. Okay, but maybe that's the problem then. So some data protection law, right, starts to speak to, or at least attempts at data protection law starts to speak to, well, you can collect data for a specific purpose. You must collect data fit for that purpose and that purpose alone. And you must not use it for any other purpose. So if I want to collect data to do, say, a bias assessment or to do some mitigation, is there a way to do this in a way that gets only used for bias assessments and not for something else, right? So then, in fact, this is a reasonable question. For one approach has been, let's not collect data on demographics. Let's build a model to predict someone's demographics from whatever publicly available data we have as a proxy. So this thing called BISG. BISG was used, for example, by Stanford and the IRS to sort of determine that there was a disproportionate amount of auditing of black taxpayers. You don't submit your demographics in your tax form, but they were able to do this using this proxy. Now, these proxies have their own problems, and you want to fix them, and that's something else we're working on, right? I have a paper on this right now. But that's one approach. Another approach is, no. What you should be doing is collecting the data, putting in some kind of sandbox or some kind of protected sort of cabin where only the auditors can look at it and no one else can look at it. So how can you do that? This is where I think the power of technology and of computer science to bring solutions to these questions is very important. And that's why I keep coming back to this point of reimagination. We are stuck in these dilemmas, these conflicts, because of the affordances of the technologies we currently see as available to us. I am often in conversations where I'll say, we could build this differently. We don't have to do it this way. There's all this other cool tech out there. We could do this. We could imagine. I have colleagues, for example, who built a system that will automatically delete data after 30 days or whatever number you say, just cryptographically. That's a cool thing. You can use cryptography to do all kinds of cool stuff like this. We just have to know the right questions to ask. And that's where this conversation is so important, right? It's the socio-technical system you're trying to build. You have these concerns about privacy. What can we build to support what we want? I think that's really important because we are, I think, stuck in the set of affordances given to us by the technologies that are being sold to us and not by the ones we could be building for the next generation.
I'm also thinking about, you mentioned the morality of the market, right? So there are the morality of the market, and there's, I'm sure, for every company that wants to do the ethical thing, they're thinking about the competition of somebody else that doesn't care and is going to ask for forgiveness rather than permission. So, what safeguards would you propose to help prevent some of that? And especially, businesses are going to come down to either who sells them the most or what's going to be cost efficient the most.
Right. So I'm inspired a lot by this whole idea of these different mechanisms that we use to sort of manage, right? Larry Lessig talked about this, right? This idea of we have laws, we have markets, we have norms, and we have code, right? And they all sort of work together to organize society. I think of markets as as a different player in the space, but one that we cannot rely on solely to incentivize corporations or other entities to build the software we want. We need a combination of things. We need laws that force people. We need regulations that force, and I think the AI Act is going to show us the possibilities and the limits of that approach. If we do eventually ever pass any kind of broad-based AI regulation in the US, we'll see that too. Right now it's only very patchy in the States. So that's I would say, an immediate term thing. I think markets will start to react. I think we're already seeing markets start to look at what it will take to build the compliance needed to work with the AI Act. So that market's going to adjust. But I also think a more long-term goal, and this is because of my vantage point as a professor, is changing culture, right? It's changing attitudes around what is acceptable to put out in the world, right? There was if you're a software engineer and you don't do proper unit testing in your software, you will be considered a bad software engineer. You will not keep your job very long if you don't properly test your software before you put it out. Okay, but then how much more work is it to do bias mitigation and testing? I want to teach students, and I'm doing this now, that will go out in the world and view not testing for biases as just a bad software practice. I think that's a reasonable thing to expect. It's not hard to do within the current framework of how we do technical development. It's just one more thing to add to the list. And I think that's another approach to thinking about long-term change, right? So I think of all of the things that operate in different timescales. I think culture change takes the longest time, but it's the most permanent if you can sort of do it. So if we think only about markets, I agree with you. Right now, there's very little incentive. There's one player breaks the agreement and it'll go. That's why we need a combination of things at the same time. We need industry standards. We need best practices. We need what NIST is doing, putting out these practices, saying if you do these practices, that's sort of blessed and is reasonable. We need actual regulations to put some teeth on them, and we need all of it.
You talk about putting values at the center of these kinds of conversations.
Yeah.
Do you imagine that there are circumstances, therefore, when your values are in such conflict or conflict with the available data,
Yeah.
right? I think about what you said concerning pretrial release algorithms. That you're at an impasse, and if you're at an impasse, then what happens? If
I mean, the only reason there's an impasse is that if you feel like you have to deploy the algorithm. If one of the options available to you is, let's not deploy this algorithm, you're not in an impasse anymore.
Except, and maybe you'll say that this is just all about values. The reason we turn to the algorithm is because the existing mode of decision-making,
Right.
human decision-making,
Right.
is itself flawed,
Right.
and in some ways even harder to test for bias.
So then the question is, do you have evidence that the approach you're proposing, the algorithmic approach, irrespective of the ways in which it might conflict with your values, is actually doing something better? That's the question. That's a question that I think is natural to ask. It's a reasonable question to ask, but it's surprisingly never asked that much. I don't find it asked as much as it should be. Is this actually doing something better? Versus, is it doing something? Versus, oh, here's shiny code, can we use it? I mean, I often find, I mean, I don't mean in the risk assessment category, I think, for one thing, because it's had so much attention, it's probably one of the places people are most careful about thinking about deployments. There are other places where algorithms are deployed where the rationale is, yes, it's more rational and more intelligent, but you poke a few steps deep, it's like, yeah, it's cheaper. We can fire a bunch of people, and this is much faster. And I actually wish people would be more honest about that. If you said you're doing this for cost, that would be a much more transparent discussion to have. And you wouldn't be dressing it up with these claims of rationality. Because I think a lot of times the rationality argument around algorithms is a fig leaf for the real argument, which is scale. Because there's no evidence for that.
I can talk really loudly if that's okay.
I can hear you. Oops.
I'm good. I'm a teacher. I teach here right afterward. So I'm intrigued by the answer that you just gave to Professor Chanenson, because if I'm understanding you correctly, the dilemma that Professor Chanenson set out is when you have a question between a biased human decision made by a judge, let's say regarding pretrial detention, and a biased algorithm, you are recommending that you just weigh up which one does less harm, which one has less bias.
I'm saying that's one way to approach the question, definitely, yeah.
And I guess that's what I want to push back on, because
Yeah.
that seems like just a thoroughly consequentialist way to approach this problem.
Okay, sure.
And there's a vast philosophical literature about these issues where people argue that there is a deontological duty for a human decision to be made, particularly when we're talking about an agent of the state, the force of the state locking up its people, that the right to a human decision is not just a matter of sort of a consequential weighing up of risks, harms versus something that will do less harm, but instead there's sort of a right, a duty, a sort of whole different framework of thinking about these moral questions. And I'm just curious to
I mean,
know
you're not going to get any
about
disagreement
that.
from me. The fifth principle in the blueprint for the AI Bill of Rights is exactly what you said. So I don't disagree with you at all. But I think your point about, you're right, that the weighing of harms and benefits is very consequentialist. And I didn't mean that's the only way to do it. I'm saying you have to at least have this discussion about which one should you choose. And I guess maybe my bias is from a place where I'm seeing that discussion just not happening at all. The assumption being that any piece of tech you put in place is obviously going to be better. And this is unfortunately a lot of the places where I'm like the, excuse me, do we know how this works kind of person in the room having discussion. And I don't think that's true in 2024. It has been true for a very long time. I think there's been enough pushback now, there's at least a willingness to stop and think. But there's a paper, a very fun paper that came out a few years ago that some of my colleagues had written called The Fallacy of AI Functionality, which sort of documents all the ways in which claims about AI systems being functional, forget bias, forget anything, just working, are in fact lies and are unsubstantiated by any evidence around them. And they have both a taxonomy and a long list of examples of this. And so that's kind of where I'm coming from when I make these points. But I think everything you're saying is, I absolutely agree with that. That is the discussion we should be having. What is it we want the agents of the state in this case to be doing? What do we believe as a society, as a community, is the right thing to do? Centering those discussions and pushing the tech slightly on the side is where we should be. But often the framework is like, okay, here's the tech, now we discuss around it.
Can I say one quick thing in response then?
Please.
So for anybody who's a policymaker out there or cares about education, I think the conversation that we just had illuminates why the push towards STEM and technology and mathematics and science, while important in many ways in our society, is problematic, and that we should be promoting the humanities. We need more philosophers in our discussions, basically, is what it comes down to.
No.
And if we're not educating philosophers, then we're not going to have them in the discussion.
And I should say, one thing we do at Brown, not to sort of thing, is that we try very hard to do this. I'm actually running a 3-year collaborative project with my colleague in the history department, looking at sort of these concepts that have been teed up by AI and how the humanities have learned to understand these concepts. What is the model? What does it mean to do things at scale? What is context? And how to bring those voices into the picture. So I agree again.
Maybe I'm asking a similar question, but how can regulations ensure safety without stifling the innovation around us?
So it's an interesting question because I think there's a premise there that ensuring safety will harm innovation. I think about all the innovation in seatbelt technology. There's been a lot of innovation in how we use seatbelts. It used to be one way, there are all these different techniques. Now they even have these weight sensors that tell you if someone's sitting there, the seatbelt time goes off if someone's sitting there versus not, and so on. You can have innovation in the realm of safety. There's a lot of interesting questions to, for example, how do we do efficient auditing of algorithms? How do we build more explainable systems? How do we sort of work with, especially the large language models, how do we make them more explainable? There's a lot of innovation to be done there. I don't think putting in regulations or putting the regulations limits innovation. It just shifts the innovation away from, speed at all costs to something else. And I think that's what people have a problem with. Not so much that there can be no innovation. There's plenty of brilliant minds waiting to think about these questions and needs incentive to do it.
So let me ask one last question that kind of recognizes where we are in a law school. You've dealt with technology policy in a variety of settings and undoubtedly dealt with a lot of lawyers.
Oh, yes.
and that's been the highlight of your career, I trust.
Absolutely.
So what is it that you find the most useful contribution from the lawyers and the most frustrating?
So I didn't know anything about how the law works till I started talking to lawyers. So for me, the most useful contribution is the intricacies and the complications around the law, around policy, and around how I think things that seem like they should work don't work because of what happens next and what happens next and what happens next that people in the world of law have studied over a long time, right? There are not too many policies one can come up with today that someone hasn't tried somewhere before and that we've seen how they play out, we've seen how the courts will react. Understanding the systemic approach to this, right? Okay, you can do this, but what are the courts going to do when you do that? How are they going to react? How do you bring in the role of the judge? These are things that I have learned a lot from lawyers because my instinct is like, oh, let's build this thing that just works. Like, no, you gotta find a way to hand off to people who will then make the overall decision-making, because the decision-making apparatus, especially in the legal system, has a certain value and structure to it, and you need to incorporate this because the law is not going away. So that's what has been very useful for me. I don't think anything's been frustrating. It's just there's a normal sort of back and forth of people from different disciplines trying to talk to each other that can be a little frustrating at the beginning, but it's not a big deal. I think one thing maybe I'll change the question a little bit and say one thing I have found to be useful to convey when I'm talking to lawyers about technology is that it is far more mutable than people think it is. That we can change and rebuild and build different widgets in ways that people who don't have experience with technology, which is often a lot of lawyers, don't realize. When someone says, well, we're stuck with this particular this particular differential privacy technique, like, no, in fact, if you can say what you want, we can go and build something different. And that technology can evolve, it can adapt. And so I think that trying to convey that possibility, that the options are much broader in our technology space than it looks like, has been a useful thing for me to do, to say that our space of levers is more than we think it is. That's helpful.
Wonderful. All right. Well, thank you very much. We're really grateful for you.